I think for agents, it's kind of very new, but my thinking is that causality will start becoming very important because agents will start interacting in the real world, right? Or even in the web world, they're interacting with other people. And so now these notions of action and reward and sort of what is behavior you want to optimize, what is behavior you want to penalize, all of these are at their heart causal abstractions. Hey, which agent is the most useful here? Which agent should be rewarded more? Or counterfactual notions of blame. If there are agents in a system that are not doing well, you probably want to remove them.
We have some very interesting papers out there about agents and causal modeling. There's a paper from Richens and Everett, guys from Google DeepMind, who presented a theory of how agents can learn robust world models. How do you think, you mentioned counterfactuals, these ideas are mainly about interventional distributions, so making an intervention in the environment and learning the response. How do you think about causality and those new questions about causality that you think might emerge with agents?
Someone else did experiments of these different graphs and gave us this axiomatic data about it. And we are just learning from this passive data to build causal reasoning. They will find statistical shortcuts, and maybe that's what they're also doing for this axiomatic training. Because remember, we observed that for, let's say, graphs of length 10, they do well. But their performance does taper off as graphs of length 14 appear.
Hey, Causal Bandits. Welcome to the second season of the Causal Bandits podcast, the best podcast on causality and AI on the internet.
He believes that data tells stories, and he wants to tell causal ones with his research. He sees causality as a goal, even if we don't always know how to achieve it. From open source contributions to societal impact and back. Creator of DoWhy and principal researcher at Microsoft Research India. Ladies and gentlemen, please welcome Dr. Amit Sharma. Let me pass it to your host, Alex Molak.
Hi, Amit. Welcome to the podcast.
Hi, Alex. Thanks for inviting me.
Thank you for finding time for this conversation. I'm super excited about this one, partially because my adventure with computational causality really started with DoWhy. DoWhy was one of the first computational devices or libraries that I used when I was in the beginning of my journey. And you are, for those people in our audience who don't know this, the original creator of DoWhy. But before we move to a conversation about DoWhy that I would love us to have today, I want to start with something else. A few months ago, all the hype was around large language models, and today it's agents.
Yeah.
What is your thinking about causality in the context of what is happening at the forefront of machine learning, or at least machine learning as we can see it in the more, let's say, popular media?
Yeah, so I think it's been so fast that sometimes it's hard to step back and sort of form thoughts. But I can answer your question in two ways, right? So at least I have a better understanding of LLMs, and then we can go to agents. So I think what LLMs have shown us is that causality was always requiring two things: domain knowledge and then discovery and reasoning. And I think our field spent a lot of time on the second one, and given some data set, how do you get good graphs and then reason over them? But we kind of left the part about domain knowledge very vague, right? That someone will come and give the domain knowledge. And what large language models essentially showed us is that there are ways of learning that domain knowledge. And for a lot of cases, if you're able to get that domain knowledge right, you may be even able to do reasoning in many situations, right, which do not require you to have data. So that's how I think of at least large language models, right? Whenever people show results and say, oh, amazing, this is reasoning, right? So I still think it's a lot of domain knowledge plus some sort of generalization that's enabling it to do what appears to be reasoning. But the lesson is that for the future of causality and the future of causal inference, we have to take both into account, right? And think about how do we also supercharge our methods for getting domain knowledge correct and inserting them into real world algorithms. I think for agents, it's kind of very new, but my thinking is that causality will start becoming very important because agents will start interacting in the real world, right? Or even in the web world, they're interacting with other people. And so now these notions of action and reward and sort of what is behavior you want to optimize, what is behavior you want to penalize, all of these are at their heart causal abstractions. So maybe in the training of agents, causality may not appear as much. It may just be plain RL, where you just have some rewards in mind and you're optimizing them. But I think the moment they start interacting with other agents, or they start sort of doing stuff collaboratively, we'll start having to grapple with questions about, hey, which agent is the most useful here? Which agent should be rewarded more? Or counterfactual notions of blame. If there are agents in a system that are not doing well, you probably want to remove them or improve their functioning over time. So I feel in the future, especially with agents, there'll be new kinds of causal questions that will come up. I think perhaps a little bit like social science, but I think a lot more understanding about designing these systems from the ground up so that they behave in the ways that we want them to behave. So that, I think, would be one critical part in which causal thinking would come. And I think maybe some training algorithms also that might be motivated by that.
We have some very interesting papers out there about agents and causal modeling. There's a paper from Richens and Everett, guys from Google DeepMind, who presented a theory of how agents can learn robust world models. How do you think, you mentioned counterfactuals, these ideas are mainly about interventional distributions, so making an intervention in the environment and learning the response. How do you think about causality and those new questions about causality that you think might emerge with agents?
Yeah, so I think those papers are some of my favorite ones, but actually they are kind of answering a different question, which is that if you don't think about causality, how can you still learn some principles, or how can your behavior mimic what an ideal causal agent would have done? And I think it's quite instructive to sort of understand the import of those papers to be able to also understand how causality can now help in this new sort of ML future. My learning from those papers was that there are different ways to learn how to act correctly in a system, right? At its core abstraction, right, causality is about making the right actions that would optimize the right outcomes. And what they showed is that if you just have enough diverse environments for an agent to operate in, even if that agent is just trying to do well in all those environments, that's only their objective. They have no knowledge about a word model. They have no understanding about anything else. In the limit, like, they would actually start doing actions where that would mimic something that a true causal agent would do, which had the world model with it, right? And they also have some interesting sort of theoretical abstractions, which can say that you can even recover the world model if you just observe their actions, right? So if you just observe what they're doing, it's possible to understand the world as well. So to me, I think these are new results that are emerging, which are just showing us the power of data, especially diverse data. There's a bunch of other work also from Sholkov's group, which talks about exchangeability and how just the fact that you now assume you have exchangeable data, which is similar to data from multiple distributions, you can now start doing much better in discovering causal relationships. So I think it's a very promising trend in thinking about a new kind of imparting causality, right? Like, what are the diverse domains, or what are the diverse ways in which I want to expose my agent, so that by itself it's going to learn what's the optimal relationship between variables. That's the one that helps it do well in all the environments. And I think this is again sort of pointing out to what I was saying earlier, right? Like, in my past 2 years, I've just spent thinking about what is it about causality that has changed now, or what is it about causality that I didn't fully understand before LLMs. And I think the one answer that I can give it is a very clear answer, is that there are multiple ways to reach a causal agent. I think pre-LLMs, there was some sort of a consensus where the idea was you have to think about the right mechanisms, you have to think about the right graph, you have to have the right biases, inductive biases into the model, which are derived from causal principles. And that's the way to get causal actions, right? But now I feel many results are showing, like, now there's clear evidence that there are other ways as well, right? So one of the ways is just collect a lot of diverse data. And as long as you have done a good job, of course, there's no way to verify. So it's not a very intellectually satisfying exercise. But if you've done a good enough job of collecting enough diverse data, we have both empirical and theoretical evidence now that you can actually generalize and you would be able to learn at least the causal actions, even if you have no idea of the causal model. And then there are other kinds of thought experiments that you can also think about, which is another way of looking at causality is just generalizing from a set of rules, right? So if you think of, let's say, rules in physics, this is how many LLMs today appear to also answer causal questions, is because they've read books which have told them theorems in physics. And so if you ask them to, let's say, predict the velocity or momentum of an object given some kind of input state, one way of solving it is to go from first principles, discover the relationship of how objects move, maybe discover the Newton's law, and then solve that problem. The other way is to cheat and just learn from what Newton has already told you and just apply that equation and again get the right answer, right? So I think that's the other way of getting causal actions, is that you just build your foundation on domain knowledge, or you build your foundation on many theorems and many axioms that have been proven to be true in the world. And so even at test time, if all you're doing is applying a bunch of variables in an equation, it appears that your actions are consistent with what a causal agent would also have done, right? And so I think that's perhaps the summary of my reflections on this topic, that I think there's maybe a third way as well. We don't know. Like, there are many different ways of reaching good causal models. Data augmentation and domain knowledge definitely have been shown, but I'm now looking for more ways to do this in a scalable way as well.
There's also a question if what you call cheating here, quote unquote, is really cheating, right? I remember our conversation with Andrew Lampkin and also from Google DeepMind, where we were discussing the idea of behavioral cloning. And this is also how we as humans learn, right? We also read books. We also observe our parents as children. We learn how they act in certain situations. And so that's certainly a way to also speed up our learning, to learning some valid strategies. At the same time, we of course know that there is no guarantees in behavioral cloning, because there is no guarantee that the agents that we are observing are actually correct, right, or optimal.
I said cheating because it's kind of having access to some theorems or past information. But a very nice thought experiment is regarding the gravitational constant. Now, of course, you and I know that it's different. So it's different on Earth, it's different on the moon. But now imagine if we are in the classical causality world. I give you a lot of data from the Earth, right? And maybe I give you a little bit of data from the equator. I give you a little bit of data from the poles. And there's a slight difference in gravitational constant there as well. So in the classical causality, what we are hoping is, by giving you enough variation that I can on Earth, and let's say I'm telling you the mass and weight of every object in all these places, I'm hoping that you're able to discover that there is some G, which is the division of weight by mass, and that it varies across in different parts of the Earth. So when I take you to the moon and I ask you to do the same thing, you would perhaps do some more experiments, again learn the G and get the answer. But this is a much difficult learning process, right? It's most likely many models might just learn G as the average of whatever is on the equator and the poles. And then when you go to moon, they'll just apply that, right? And they might fail. So I thought in the classical causality, it was very ambitious, and we were asking it to do a much harder task of generalizing from this knowledge. Whereas in this new world, models are capable. I would just perhaps teach it the gravitational law and say there's something called G. You have to look out for what that G is, and G varies by planets. And then now that you know this information, not only you can do a better job at Earth, because on Earth you can kind of use your statistical data to estimate it. But the moment you go on the moon, you would also suddenly realize that your statistical data is not enough. You'll just make maybe a few more observations on the moon and be done with it. I guess that's how humans learn. So it's a much more attractive way, I feel, of trying to get to the dream of a causal model, right? Or a dream of an agent that can act causally. Maybe it's not cheating. Maybe it's just a better way of structuring the initial knowledge that the model starts with, so that it doesn't have to do really hard tasks to do well. Like, it can actually know some of the context and adapt easily.
What do you think the contemporary agentic frameworks are missing the most today?
It's very early, so I think there's a lot of things missing. I'm just thinking about, maybe I'll say verification is what I think is the biggest thing missing. So most of the contemporary agentic frameworks have been built in, I would say, slightly well-controlled areas like coding, where there are verifiers like the compiler, which will tell you whether you're good or not. Or in terms of calling APIs, where again, if the API fails, there's a very clear signal that the API has failed. And so agents can adapt and then they can backtrack and do something else. Or there are cases where the agents are just told to write a research report on causality in the last 5 years. And they do something and then the user at the end just says yes or no, right? And they would give some feedback. I think what's really missing is how do you take these kinds of frameworks and apply them to these vague problems in the real world where maybe even humans cannot give good rewards to these. And anyways, I think that's not scalable, right? So we need some way of creating verifiers for new domains, maybe just for the outcome to begin with, but then also starting to maybe give some kinds of rewards for different actions that the agent is taking, right? So I'll give you two examples. Like one is very simple. The other is the cutting edge of what I think causality could do. Very simple example would be like summarizing a meeting, right? So we are having a conversation, there'll be a transcript. We can imagine agents to, or even LLMs to kind of summarize that. And there you can have all these kinds of different rewards. Like, is it precise enough? Is it recalling all the important stuff? What is important to Alex? What is important to Amit? And so on, right? So even here you see that there's so much of verification that needs to be done that if done well can only help you improve the output. But if not, then I think the agents can go haywire. And I think the more kind of harder example is in doing science itself. Now, suppose you have agents which can generate literature reviews. They can read the literature. The next step would be they can suggest experiments. And then you would want to start thinking about how to give feedback to these agents so that they actually start designing better experiments and so on. So thinking about verification in a more holistic way and like how do you create verifiers for all these kinds of scenarios, I think would be a big leap, right? Because once you have that, you can also train better agents. You can also test them at test time. But I think it's kind of a art and science where based on each domain, you want to think about what properties need to be verified. Can you actually create some kinds of causal systems that give you necessary properties to prove in that world? Yeah, so I think that's what I think is missing right now.
Verification is also one of the very fundamental problems in causal modeling.
Yes. Yeah.
In DoWhy always had some ideas on how to verify models, maybe not directly verify, but how to try to falsify them. In recent, I think 2 years, you added more modules to DoWhy and EconML that can help with these tasks related to assessment, evaluation, verification. Can you tell us a little bit more about this and what ideas are at the base of those solutions that you propose in the library or libraries?
Yeah, so I think for causal inference, it was more of a clear problem because you would get some estimates from observational data. And without doing a randomized controlled trial, there was no way of knowing how good they are, right? So at least I think in the agentic world, the problems are simpler. So you can imagine having some simulator or some causal model that can at least verify what you're doing. In DoWhy, our question was, how do you evaluate this causal simulator? Who knows whether this causal effect that you've got, who knows whether your graph that you've got is correct or not? And to me, I think when Emre and I were building DoWhy, I think the first 3 steps of the pipeline were very clear because I would read Paul's book and he would clearly say that it's not just about estimation. It's about thinking about the graph. It's about thinking about identification. And all of those things can happen without the data. So the first 3 steps were clear, right? For this last step, which was refutation, which as we finally coined it, we had to actually look to how economists are doing it. So when I was at Microsoft Research in New York as a postdoc, I had the good fortune of being in a lab which had computer scientists, but also economists. And also a lot of visiting economists who would come and sort of, I would get a chance to talk to them. And I realized that in the way studies are evaluated in economics and social sciences in general is that you present something and you go to seminars and then a lot of good researchers will give you feedback. Hey, have you thought about this? What if this part of your causal model was wrong? Hey, have you done that robustness check? And that you should really try to check whether your placebos are really placebos or not. And it was only after a bunch of such sessions have happened that you would finally write your main paper and kind of submit it and do all these robustness checks, right? And so that's what we have tried to include in DoWhy since the start. I think initially we tried to include a sensitivity analysis, which are simply just thinking about what happens if you had missed some unobserved confounder. Slowly after that, I started moving towards more not deterministic, but like objective, quote unquote, tests, which would give you a yes or no answer. Like, so these are like significance tests. And here I drew a lot from biomedical literature because they had this idea of negative controls. The idea was very simple. Like the moment you find something amazing in your lab experiment, you want to make sure that it was because of the reagent that you think is the cause and not because of something else in the lab at the time, right? So a negative control would simply mean you would remove the things that you don't think matter, redo the experiment with the same reagent, and still see if you get the same result or not, right? So we kind of ported it back to causality. So we created situations where I can add a random common cause to your analysis, right? And so that's like something that should not really change. Or I can replace your treatment with a placebo. This is also something you can do automatically because there's a column called treatment, you just replace it with a random variable. And I think more recently what we've been trying to do is to marry these kinds of ideas with real data so that the tests just become more and more powerful. So in one of the methods that we added, we created this notion of a dummy outcome, which is very similar to a placebo treatment where the outcome gets randomized. But now you can do something special where you can still have the outcome as a function of the confounders, but not as a treatment. And actually, this is very simple to do because I can cook up any function that's a function of all the confounders and call that my new y. And by definition, I know that this is not caused by treatment. And so now if you create such a dummy outcome, you should again get a causal effect of 0. And so we start seeing that now you add these kinds of tests. Now, like some of the methods, especially at so lower sample sizes, start to struggle. And some of the more recent tests actually have been added by contributors of DoWhy. So there's one test which tests the overlap of the treatment across different confounding variables and tries to give you some sense of like where you can actually trust the estimates and where there's little overlap. So that was done by Michael Oberst, who was a PhD student at the time at MIT. And I think some of the more recent tests have also come from a team in Amazon who are now collaborators on DoWhy as well. And they've been going very hard at this problem of verifying the graph itself, right? Because so far, all that I talked about was verifying the analysis. Maybe you made some errors in the estimation or the model that you're using. But ultimately, it all starts from the graph. And so if you got some wrong assumptions in the graph, well, like good luck. So what we had initially in DoWhy was something very simple. We would just test conditional independences, right? We could say that, hey, if the graph has the structure, then there are some conditional independences that come out naturally. So let's just test them, right? But I think Patrick and others have built now much better statistical tests which try to compare the information that the graph is giving compared to the information that a completely random graph would give. And then they sort of try to give you confidence on how informative is the graph that you're getting and how well supported is it by the current data. Right? And so I think, so DoWhy over the years, I think, to be honest, is now I think of it more like a community project. So I think when I started, it was more of this initiative to kind of create the right API, get the right functions in. But I think now much of the interesting or the more recent work that you might be seeing in DoWhy is really like great collaborators or contributors who've just built great methods and then they've included them in DoWhy.
How has it all started with DoWhy? What was the breaking point for you that you decided and then teamed up with Emre to create this library and make it public?
Yeah, well, it wasn't like something that we consciously decided. I think maybe going a little bit back, this this all started, I was working on causal inference in the context of recommender systems for my PhD and also for my postdoc. And at the time, I was very new to the field. And I remember I would spend days reading Yudia Pohl's book. I would also read potential outcomes from statistics and other books. And it would be really hard at times. After, I think, a few months, I finally understood that what these books are talking about are very simple concepts. And by the way, I'm talking about Pearl's Causality book. Like the book of why was still not out. So it was the book that's really hard to read for a beginner. So I think I had two realizations, right? So one was that the concepts are very simple. Right? The concept of a backdoor and controlling for variables is a very simple idea, but they are presented in these books in a very formal way. And that makes it very hard for people to understand, right? And it was pain for me to also go through and finally do some of my experiments that I wanted to do. The other part I was also seeing was that the potential outcomes framework and the graphical models framework, when I entered the field, I got a sense that they are very different. And at the start, you have to choose one, and then one of them is better maybe. But as I read them, I realized that they're the same. I mean, no, okay, they're not the same, but I think they're solving the same problem, but with a different lens. And so in some sense, they are compatible. Like if you're thinking of how to frame your problem, graphical models are great because they give you a interpretable way of communicating your assumptions. You can do calculus and backdoor on them. But the moment you turn to estimation, once you've found your estimand to estimate, there are some very nice methods from the potential outcomes literature. Right? The propensity score based methods came out of the potential outcomes framework, and they are excellent ways of actually working with data and estimating things. So I think it was really the combined sort of confluence of these things where I felt like if I'm doing a next project on causality, I don't want to go back to these books and kind of grapple with them until I find the right estimand and then sort of re-implement some estimator on my own. I thought like, would it be great if there's just like one tool that helps you do all these steps at once? So, and then I contacted Emre, and I think he was facing similar problems. He was also working on causal inference for longitudinal data. And so we thought that, let's just do it. So I think initially we were just thinking of doing it for ourselves. Like we wanted something that is reusable for us. And then, of course, we open sourced it, and then I think a lot of people liked it. So that's how it all started.
And so what's next for DoWhy?
So two great things happened over the last couple of years. Right? One was the collaboration from Amazon, which made us realize that, hey, it's not just about a bunch of methods that we put in. Maybe this can become bigger, right? So we created a new GitHub org called PyWhy, which is kind of where DoWhy sits now. So it's no longer associated under the Microsoft account. I think it's now a much more global community of people. So I think one of the things that has happened through it is that we are trying to build a causal ecosystem of solving any causal problem, right? So DoWhy was focused on effect estimation. I think then we also did root cause analysis. But nobody starts with a graph, right? Maybe you start with the data. And so you need discovery. So that's where Causal Learn, which is a package from Kunzang's team. He kindly agreed to also sort of make it interoperable and put it under the PyWhy organization. And then EconML, of course, from MSR Newton Lab, they also collaborate with us heavily. And so they also came in. So I think one of the next directions for us is to make the process of causal inference with data as seamless as possible, so that you don't feel as if you're interacting with DoWhy for this project, you're interacting with Causal Learn for some other project. You just have this PyWhy verse, if I may, and then you just interact with that and you say what I want to do, and these libraries under the hood talk to each other and help you execute that task, right? So I think that's the first level of vision where we're trying to bring these together and build some notebooks to show people what's possible. And basically you start from your data and then you get a notebook that combines the analysis across different angles. The second thing that I'm very excited about is a new library that we have started called PyWhy LLM, which is like the higher level abstraction of the same thing. Right now, of course, it's basically just showing that LLMs can do causal discovery, or in the sense of getting domain knowledge for your problems. But I think the way the direction in which we are going with that is that this makes it now even possible for doing causal inference for non-experts, right? So think of citizens or general public, right? If I have a question about, let's say, some medicine, right? And my doctor has recommended it, and I just want to understand what's the outlook in science about it. Or actually, that might be a much more serious question to ask. I don't think we're there yet, but maybe something more simpler, like you're trying to understand what's the effect of some kind of intervention in schools, and then how does it help affect your own learning, what kinds of things you should learn, and so on. Right now, there's just Google, right? Or maybe now there's ChatGPT as well. But what if we could make a much more causally aware version of a system like that, right? And so that's why we want to move PyWhy LLM to, where we are solving causal questions, but the input is text and the output is also most likely text. And within the loop, we are using all these advanced libraries and all these advanced tools that we built in Causality. And so for questions like what should, let's say, be the optimal coffee for happiness, right? Maybe there's a way we can look at all the research papers and give a summary that maybe doesn't matter. there's enough evidence on the contrary to both sides. And maybe for other things, we would say that, oh, how do I optimize the sensors in my factory so that my factory never has any faults, right? In that case, maybe we would come back and say that you have to give us data, and then you give us data, and then we do all that analysis for you, right? So I think that's the kind of dream of PyWhy in the future. First is to enable experts to do the analysis that they want without having to think about which library to call. But I think ultimate goal is to really help anyone sort of engage with causal questions. And if you remember, like it comes back to the first question you asked, right? That I now have a much more broader view of causality, right? So if someone is asking a question about, let's say, coffee and health, probably it doesn't require any data, right? All it requires is some agent to go look at all the research papers, provide a good summary to someone, and provide it in a very accessible way. That's one end. At the other end is some scientist or some industrial operator who finds a lot of faults in their, let's say, energy system. And so they're thinking that, hey, let me ask this PyWhy agent, why are there so many faults in my system, right? Can you help me? And then, of course, you'll have to give us some domain knowledge. You'll have to give us some sensor data. But that's the only input you give us. And the idea is that everything else helps you get answers to your questions.
Are there any particular bottlenecks that you think this integration with LLMs could address?
I think the biggest bottleneck is the graph. That's the overwhelming feedback we have got for DoWhy, is that DoWhy starts with a graph. How do I get a graph for my system? And that's true. I mean, except for like some situations like I talked about this energy system, right? Maybe there you have a graph because you've engineered the system. But in most cases, yeah, I mean, it's really hard to get a graph, and it's really hard to convince even yourself that your graph is correct. So I feel that perhaps is what we are focusing on in the short term, is to really make it easy for people to generate plausible or credible graphs for their problem. And the other thing that is also a bottleneck is in kind of thinking about ways to test your system. So like I was giving the examples of negative controls, right? Of course, in DoWhy, we can simulate them, but DoWhy also allows you an option to specify which variable is a placebo or which variable is a dummy outcome. Now, again, I mean, in the real sciences, it takes an expert to say that, oh, actually, this outcome also happened around the same time, but it happened in a different city. So I can call it a dummy outcome because it has all the same confounders, but it doesn't have the treatment that I'm looking at, right? And so we are finding that LLMs are also good sometimes in giving these kinds of suggestions on what might be good refutation tests to run. So I think in the short term, we're just focusing heads on just these two problems. So one is, how do we make the process of creating the graph as simple as possible, which means that the LLMs will give you a graph that you can critique as an expert, and then feed it to DoWhy. And the other thing we are looking at is, again, the second most common feedback perhaps I've got about DoWhy is that you guys have so many refutation tests. I don't understand what they're doing, and I don't know which one to trust, because sometimes one of them works, one of them doesn't work. So what do you do, right? And so even there, we are hoping that the broader PyWhy LLM could actually guide people towards the right tests to run and interpret what they need, and hopefully build stronger tests for those problems. So I think that's where we are really going towards in the future.
So that's very interesting, because what I also hear from my clients and prospects in industry is that LLMs are really useful in making the process of building the initial graph much faster. So they help streamline streamline the process. That said, LLMs are still limited mainly by the fact that they hallucinate, and they hallucinate in ways that are often very, very difficult to predict. So they might hallucinate in a case of something very complex, in the case of a very complex task, but sometimes they can also hallucinate in the context of a very, very simple task that would be obvious for any human. So full automation seems not really realistic today, at least in the context where accuracy matters or the cost of error is high. But when we think about LLMs and causality, we can think about using LLMs to streamline the process of causal modeling. But we can also think about ways how to use causality to make LLMs more robust. And I know that some of your research with Aniket, for instance, focuses on these ideas. Could you share a little bit with our audience about this line of research, and what do you think is important in this line of research?
Yeah, definitely. Yeah, so I sort of keep straddling between these two spheres, right? So one is how machine learning can help causal inference and causality. So that's where DoWhy and I think a lot of the refutation tests come in. What you're pointing to is the second strand, which is how can causality help machine learning. There, I think I've over the years learned that it's a really sort of a hard question to tackle, because often what matters in machine learning is like some accuracy on some distribution, whereas what often causality targets is accuracy on some worst case distribution, which may not happen, right? Or it just happens very rarely. So this project with Aniket Vashisht, one of my research fellows here at MSR India, and also Vineet Balasubramanian, also a colleague. So here we were looking at how, so it's clear we just talked about how LLMs or AI can help causality, right? That was very clear. Now, how do we reframe this question? How can causality help machine learning or LLMs, right? And so the previous constructs that we had that, we could add a regularizer, which is informed from causal science, was not really making sense here because there was so much data. We don't even have control of all the data and how these models are trained. Then I think there were some other questions about world models, like we can build world models in these systems. But even that felt out of reach because the world is very complex, right? Now these systems are no longer talking about a certain small world. It's the entire world they're modeling. That also felt out of reach. Like there's no way I could build credible things that you could add to these systems. So I think the last thing that I felt could have a future in this new era is the fact that causal reasoning, just like any other formal reasoning system, is built on some axioms, right? One of the reasons that we like causality is because it's very predictable in the sense that if you know the graph, you know many things just from the graph. And that's because we have rules like d-separation, or we have axioms like the transitivity axiom in stable causal systems, and so on. And so to me, it felt like perhaps what we can imbibe in these language models is more robustness by enabling them to learn just like causal systems work. I think the shift in my brain was like not imparting causal knowledge to these systems because that's too complicated, but imparting how to learn causal knowledge in the first place, right? And maybe if that process is what we can teach them, perhaps they'll also generalize better. And so that's the idea. The idea is actually quite simple. Just like any other formal system like logic or causality, they start with some axioms. And then theoretically, given those axioms, you can prove every true thing in that formal system. So we try to replicate that for LLMs, but for text, right? So we think about, rather than teaching the LLM, here's how you apply causal effect estimation for this problem, and maybe it'll learn how to apply that for causal estimation, but then maybe it won't do well for d-separation, right? Or maybe it won't do well for other tasks. This has been seen for math and other scenarios, right? So our question was, what if we now train LLMs to just learn the basic axioms? So one of the axioms we tried was the transitivity axiom. And the idea is that if you teach it a bunch of axioms, would it automatically learn to apply them and even compose them at test time? And if any agent can do that, like that's, I would say, the hallmark of intelligence, right? Then you can actually build new theorems on your own. You don't actually need all these verifiers and feedback that you were just talking about earlier. So I think, we have sort of taken some baby steps towards it. So currently our results show that if you train a model on graphs of size 3 to 6 on the causal transitivity axiom, it's a very small transformer model, 200 or so parameters, actually 68 million parameters. And we just give it information like if A causes B and B causes C, then C may cause A. Then A may cause C. So that's simple training data. And what we find are some surprising results. Like at test time, the same model also generalizes to lengths up till 14. Of course, the accuracy drops, but up till graphs of size 10, the accuracy is quite high. We even find that you can reverse the chains. You can do lots of perturbations to these chains, but somehow the model still is able to learn and compose these axioms somehow. And then recently we also tried it on d-separation. And so we teach the model d-separation. And then to make things interesting, we not only test on bigger graphs, where of course it works. So I think that's our first sort of state proof that models can generalize to learn these axioms, because that's the only way to solve it for bigger graphs if you've not seen them before, right? But more interestingly, the same model now also starts getting better at new tasks, which were causal tasks. So here what we did was we took a llama model, we trained it on our axiomatic data for d-separation and transitivity, which is completely synthetic, completely simple axioms. And now we apply to co-to-cause. And co-to-cause is a popular benchmark from Zijing Jin and the Sharpov group, where they're testing the ability of language models to do, like, construct graphs from correlational statements. So all you get are statements like A is correlated with B, B is correlated with C, and you have to kind of use d-separation and other things to give the possible answers to is A a parent of B, is A an ancestor of B, and so on. And so to our another more surprise, we found that these models actually do well. A llama model, which is just trained on axioms of transitivity and d-separation, which has no knowledge of co-to-cause, the base model does with some performance, but there's a significant about 20 percentage points jump when we apply the model with these axioms learned. So I think this is giving us some hope that maybe there's a different way of training causality for language models, but also more generally, a different way of imparting reasoning to these models without having any memorization constraints.
So that's very interesting. 20 percentage points sounds like a really significant difference here.
Yes. Yeah. We're, of course, experimenting. So I think we'll have an update on the archive paper soon. So I think the numbers may slightly change, but I think, the gap is high enough that it's very encouraging to pursue this direction further.
Would you say that these results are congruent with the results presented by Andrew Lampinen some time ago in the paper?
Oh, exactly.
Active causal strategies from passive data?
Yeah, so we were inspired by that paper, to be honest. Like the way we started this project was after reading Andrew's paper. So yeah, we were inspired by that line of thinking, and it's the same idea, right? Another way of saying what we're doing is that we are learning causal reasoning by just observing demonstrations of axioms, which are like passive experiments done by someone else, right? Someone else did experiments of these different graphs and gave us this axiomatic data about it. And we are just learning from this passive data to build causal reasoning. So absolutely, yeah, I think it's all inspired and in the same line. But we are just now thinking of taking it to the level of fine-tuning small language models and kind of improving their reasoning through this.
I'm always very inspired by results like this. So the results that Andrew has shown and then you have shown in your recent work.
Yeah.
But at the same time, I feel there's a little bit of a tension there, because on the other hand, we have results from Guy van der Broek and his team. He's from UCLA, where they have shown that even if we enforce the model to implement the correct logical reasoning strategy by setting the weights deterministically so that they implement the correct algorithm. And then we train this model just for a couple of runs on observational data from the same problem. It's within the distribution. The model will forget the correct algorithm and it will learn a statistical shortcut that does not generalize for the same problem.
That's interesting. Yeah, but I can also, that's consistent with how I'm thinking about this problem, right? That they will find statistical shortcuts, and maybe that's what they're also doing for this axiomatic training. Because remember, we observed that for, let's say, graphs of length 10, they do well, but their performance does taper off as graphs of length 14 appear, right? Which is not what you would expect if I had coded up axiomatic training myself. I'm sorry, if I had coded up the axiom myself, right? It would just have a constant accuracy of 100%, irrespective of how big the graph is. So that immediately points that there is some shortcuts happening. There is some kind of errors that are getting propagated. But I think the hope is that if you scale this data and if you make enough diverse possibilities available in the training data, the space of shortcuts is going to reduce and ultimately it's going to shrink, right? And so that's the basic tenet of the kind of research that this direction that Andrew and I and others are doing, which is that if you are able to constrain the space of shortcuts to a very small size, then maybe with enough diverse data, you'll be able to kind of converge on the causal principles. Of course, the downside is also that if you don't do that, right? And so in that experiment, for example, if for whatever reason the shortcuts were easy to learn for that observational data, then there's no guarantee. These systems can learn whatever shortcuts that suit them. So I'm not sure how practical even so what I'm working on is, but I think the way I think of it is that people's expectation of computing systems will change in the future. They're going to talk to us, talk to machines in natural language. And if that's the future, we have to build systems that can not only kind of chat with you in natural language, but when you ask a question that requires some reasoning or requires some kind of causal analysis, we should have systems that can also do that with some amount of accuracy. So for doing that, there's only two ways, right? One, you build a very good parser that goes from natural language to PyWhy's API, runs the analysis and gets back. Or you just build the capability inside the language model itself so that it does the parsing, it does the reasoning, and then gets back the output, right? I'm not sure which method is more better for the future, but we're just trying to make progress on both and just stretch the limits of what might be possible with just LLMs doing all the reasoning.
What do you think is the main challenge in causality today that if we were able to solve it, that would give us the biggest leap forward?
So many challenges, but maybe I'll tell you one technical challenge, and I think one more of a sociological or a field level challenge that we have. I think a technical challenge is that we really have to figure out ways of extracting the most we can from data sets. A lot of the progress in causality in the last 30 years or 50 years has been made by modeling the world. So just starting from Bayesian networks of Pearl, and then more recently, like a lot of these world models that people are building, I think, or even generative models, right? So they're all focused on building models of the world and then acting and then doing counterfactuals and so on. But I think we need kind of a model-free revolution in causality. Just like in RL, there was this model-based RL and then model-free RL. I say that because that is inherently scalable, but also as you just pointed out, right? The challenge is there are no theorems, there's no proof. There's very little theory right now. And so I think a lot of causal theory needs to get built around this kind of model-free causality. And if we can break this challenge, right? If we can build methods that not only extract as much information as possible from the data at hand, while also giving guarantees of the kind that we are expected to with, let's say, Pearl's graphical models. I would say that would be the biggest challenge. And more concretely, I think there's some work again from Sholkov's group where they're proposing the idea of exchangeable distributions as a new way of looking at causal discovery, which I really like, because all they're saying is the same, not the same thing, but at a high level, I think it's a similar idea that if you have IID data, and if you assume that you just have data from the same distribution, there's really not much you can do in terms of causal discovery. In many cases, you can't even know if a pair of variables, which direction causality flows. But if you now change your view and think about exchangeable data, which to some degree of approximation just means you have many environments and the data is coming from many different environments and getting mixed together, then suddenly you can do a lot more. And the paper shows that you can probably learn causal direction as the number of environments and their diversity goes up. So I think that area is completely unexplored, except for a few empirical studies that we were just discussing, right? And if we can sort of build this theory of, so now we don't have IID data, we have diverse multi-distribution data. And suppose the distributions go to infinity, right? You have lots of variations in your data. Now, what are the kinds of things that you can start doing? And what are the kinds of relationships you can start learning? My guess is a lot of the identification results will become much more richer once we start assuming this kind of data. And of course, to be clear, I mean, there have been work on this, right? People think of this as interventional distributions and then data from a few experiments. But I think, more work, if done in this area, could really unlock, I think the core question, it could really unlock an answer to the core question that many causal scientists get asked, is why is causality not being used for it, right? I mean, if I get this asked a lot, at least, right? If causal inference is so great, right? Why is not everyone using these tools? So that's the first part, the first answer to your question, right? That maybe we need to study a lot more in terms of diverse multi-distribution data and how to extract the max out of it, theoretically, in terms of identification results, as well as empirically. I think there's also a sociological answer to this, which is, for the longest time, our field has gravitated towards methods which inherently sort of principles-based, right? And there's an essay called The Bitter Lesson by Richard Sutton, which is one of my favorites. I think there was a time I was reading it every few weeks, just to understand what he's saying. But I think there's kind of he was talking about the bitter lesson for ML, but I think there's probably, again, I'm not sure, but probably a bitter lesson for causality as well, is that maybe causality is the end result that you want in a system. Maybe it's not always the means to get it as well, right? So in some kinds of systems, like I was talking about root cause in industrial systems, these two align perfectly. You actually have a graph of the system. You can do very principled modeling of the sensors. And so you get the means, which are causal, and then you also get the output, which is counterfactuals, which is also causal. But in many other cases, maybe the bitter lesson is that the output is still the same, but the means to reach might be varied. And so there is, of course, one group or one branch of science that we have built, which is amazing, which is this principles-based way to reach causality. My guess is that we have to unlock other ways of reaching causality, which may be not as obvious to start with. Like some of these methods, for example, data augmentation has nothing to do with causality. It's the simplest thing you would think of if you have a problem at hand, right?
That's very interesting you're mentioning this, because I think when you think about the exchangeability, right?
Yeah.
The paper coming from Jing and I think Shulkop, right? Then we have this idea that there is something that will not change between the distributions. There is something static between those different distributions. And it comes from my favorite poem from T.S. Eliot, the still point in the turning world, kind of, right?
Okay.
Our point of reference.
Yes.
And so when we think about data augmentation, isn't it the same? When we think about Jan LeCun's work in contrastive learning, for instance, and his team.
Yeah.
That's what they're trying to do, but they are trying to do it synthetically, so it's easier for us. Instead of collecting a lot of data from many different environments, they just say okay, let's just kind of simulate it in a very simple way, just by changing the image somehow, and let the model figure out what's the still point in this thing. So I think this is very interesting, and I think the same spirit is actually present in this paper that we just discussed earlier from Richens and Everett. Right? Because they say, these environments, they need to be different to an extent, right? Differences in the covariate distribution and so on and so on. But we assume that there will be causal mechanism has to be the same in all of the environments, and this is this root, this core that remains between different environments, and this allows us to understand something. When I think about it, I always recall, I don't know, you probably know the elements of causal inference, I think, from Shulkov and Dominik Jancik and Peters. And they have this Boucher, the illusion. When you look at the chair, at this chair from one perspective, you will see the entire chair.
Yeah.
But if you move your head a little bit, you will realize that these are two different objects that are spaced out in significantly, and so on. So I think this is so interesting because it goes down to something very, very fundamental for our cognition, this ability to change the perspective and see what is static, what is still in the world, and what is changing with our movement together.
Exactly. Yeah, I think that's very perceptive. Yeah, that's a great analogy, right? So either we are moving and we are observing the world and learning causal principles, or we can synthetically make the world move, like in these images and contrastive images, and learn from that, right? So I think that's very interesting, and I think it's worth kind of investing more, especially because there are some of these ideas, scale is guaranteed, right? It's just that we have to find the right abstraction to be able to preserve the theoretical guarantees as well. For example, contrastive learning is amazing. Like there's a sense in which I feel it's almost like a causal concept, because what you're saying is I don't have a causal model, so I actually don't know what the right prediction is, right? But I have enough domain knowledge to know that this should be better than this, right? Or this change should not change the outcome of the image, right? So I really love that principle. It's almost like I have some causal constraints. That's all I have. I don't have an SCM. I just know some constraints that are valid according to the SCM. And now somehow I use it to create loss functions or sort of augment my data. I'm really looking forward to how we can sort of take some of these ideas, which might appear very simple at first, but then imbibe them with the fundamentals of causality and build these combined algorithms.
Yeah, when you said about contrastive learning now, it also reminded me about the idea of testable implications coming from Perl, right? So this is like reversing the testable implications and trying to learn from this.
Exactly.
Yeah, that's beautiful. That's a great perspective, Amit. I really appreciate this. Before we close, I would like to go back to DoWhy for a second more and ask you, what was the source of the idea of structuring the flow of the library, the flow of the analysis in those 4 different steps that you have there? Maybe for people who are not familiar with the library, you can also share with them what are the steps, and then tell us a little bit more. How did you come up with this idea? I think it's a brilliant idea.
Oh, thanks. Yeah. So I think this DoWhy started around 2018, right? So for context, we already discussed how I was not happy with sort of having to reinvent the wheel. And especially as a computer scientist, I felt I learned better by doing. And so I was more used to the mode of sort of doing some things, checking out some GitHub repository, learning how it works, right? And I thought like many other people may also benefit from that. The way the steps came, I think was also out of just frustration, if I can be honest, with the existing libraries. So many of them were in R, and they would be like, oh, here's a library for matching. Okay. If I've already understood my confounders, if I've already written my equations, and if I know that I want to, and I've already decided that matching is the best method for my data set. If I've done all of that, then I go to that library and I do matching, right? Similarly, there was one package for different kinds of multi-level regression and so on. And then once I've done that, then after that, it's on me to find the right tests to do, right? It's on me to wait for the right expert to tell me that you should do this test, and then I'll do that test, and that's about it, right? So even it felt like at the time, again, pardon my language, but I think I was very new to causality. I was coming from recommendation systems. It almost felt like a dark art to me, like how economists and other experts would find out the right refutation tests to run. And I would always be bemused, like, how did this paper decide to do this test and this paper decided that this test was correct? It just felt like dark art to me, like there's no book, like what is going on? So that was my state of mind. And so I thought, okay, let's just make this more like an API, right? And my thinking was, there should be an API for this, and people should not have to sort of think so much about which step to run first or not. And so with that perspective, I think the first 3 steps were very clear. I mean, from Pearl's book as well, right? That is very logical. You start with a graph, then there's an identification step. Actually, one of the things that I really liked in Pearl's book, the first time I understood it, was that he writes somewhere that identification and estimation should not be confused with each other. Like one of them does not require data. And so there's really a big barrier between, you can do the first two steps of DoWhy, which is modeling the graph and identification without even having access to the actual data. So I think there were two principles that we used to create the final API. And I'll also use that to describe what DoWhy does. So the first principle was that the process of domain knowledge and identification should be somehow separate from estimation. People should be able to learn that just from the API, and so be able to iterate also better. So that was the genesis of the first three steps, which was like first you model the graph, then you identify. Third step, which is to estimate. We could have just merged identification and estimation because both of them are automatic. Like you can also do model graph and just say estimate. There's no user input involved. But I think we consciously made that choice to separate out these two things. And then the last one, I think I was mostly referring to scientific theories. I was almost thinking like causal estimates are also like scientific theories. They can only be disproven. They cannot be proven to be correct. So we thought like, let's just create this last API, which is API call, which will be refute estimate. And so that's how I think the genesis of the API was. And the idea was that for anyone new who's coming to Causality, they just have some data set, some problem, right? We communicate to them. There are 4 steps. Come to this library, first get a model, then identify the effect, then estimate it, and then refute the effect. And if you're not an expert, just think the maximum amount of time on the first step, which is modeling the graph. The rest of the things, you can just use the defaults. Like the library would just help you do something reasonable to begin with. But yeah, I think that was like, I think it was more like a pedagogical thing that we had in mind, that causal inference should have these 4 steps. And so how do we just make it into an API so it's very easy for other people also to follow that same process?
Yeah, and I think you did a really brilliant job, pedagogically speaking, with this library. Right. I started using DoWhy very early. I think I was either 2018 or 19 when I first started using it. And I also, I did my research. I checked other libraries, different libraries on the internet. And DoWhy, I just fell in love in DoWhy because of this very simple, very clear differentiation between identification and estimation, and then the idea that you can do anything step by step. You can plug in different types of estimators very easily, right? So you have the identified effect, and then you can just go in the loop and try different estimators, and so on. And then you can go in another loop and try different refutation tests. I thought it was really brilliant and really easy, really user-friendly, easy to apply. From people who I talk to, I often hear the same story. They just said like, oh, this is really great. Some people also are readers of my book, and they come and they say like, oh, wow, this is so clear. I was struggling to understand these ideas, and now I understand this very clearly. I understand now why we do this step separately and estimation separately, and so on and so on.
Oh, that's very great to hear. Yeah, thank you.
Yeah. And I'm very grateful for you and Emre doing this because it also just had so much impact on my career as well.
Yeah, I'm glad. Yeah, and thanks for writing the book. I think that was very useful for people to broadly understand causality and how to use DoWhy as well.
Great, thank you. I'm just working on the 2nd edition, so I'm planning to incorporate some of the ideas, the new ideas that we discussed today as well in the book. I hope that will be, I'm really confident it will be helpful for many people out there, especially when it comes to new refutation tests and model evaluation modules. Before we finish, I wanted to ask you a more personal question. Mm-hmm. What are 2 books that changed your life?
2 books. First one, definitely Causality by Paul. That's for sure. I've spent countless days in my postdoc reading that book, understanding it. And I still have it, I think, at home. Like I refer to it. So yeah, definitely that book. I'll tell you what I really liked about that book, because when I started, I could not understand the book. I'm being very honest. But I liked at the end of the book, Pearl has a prologue, which is like a segment of a lecture, a public lecture he gave on the importance of causality and like the history of causality, like going all the way to how Pearson, the statistician, was thinking about causality and how other people were doing it, right? And I think that really motivated me to understand that, wow, this is bigger than the topic that I was interested in, but this is kind of how you reason about the world, and it's possibly useful. Actually, it has philosophical components as well as it has like real scientific components. So I think for those of you who haven't read that prologue, I highly recommend it. It's a very easy read, and you can also find it online. What would be the second book? I'm trying to think of something that's not about research. Maybe I'll just say one more from research. It's a book, if I remember correctly, it's something like Causality without shoe leather. I think it was something like shoe leather statistics. It's a book by a statistician, and I'm sort of forgetting their name right now. I think the whole book was about a bunch of essays on causal research, where they were trying to explain how some of the findings that we think are very obvious, like, for example, having high amount of salt affects your blood pressure, right? So people who have blood pressure problems should not have a lot of salt. And that book just showed like it was based on some very small sample size and some flimsy evidence. And so it's really not clear whether that's true or not. So it was like a very interesting book with a bunch of essays. And I think the whole point of the statistician was to say, like they have this famous quote that there's no causality without shoe leather. And for shoe leather, they meant in the old world, like you have to actually go in the world. Like you have to use your shoe and go around and actually look at the world, talk to people and do some experiments. And only that's how it's not that you get a data set at home and then you use DoWhy and then that's how you get causality. So I really love that book because I think it gave me a very practical notion of how hard causal research is, and to be also thinking about, I think the kinds of ideas we discussed, right? Verification, refutation tests, they're all sort of trying to get shoe leather into DoWhy, right? Because people using DoWhy are not really going out of the world and doing experiments, but maybe these tests are kind of helping them sort of avoid some of the gotchas that they might have.
What's your message to the Causal Python community or Causal community more broadly?
I would say it's a really exciting world. I think the space of possibilities for causality were kind of steady before LLMs. I think after LLMs, it's exploded, right? I would say now more than ever, it's perhaps the best time to enter causality with fresh ideas and look at both sides, right? How causality would help make language models more robust. And again, I mean, if you don't have the resources to actually train models, you can also think about what we discussed early on, which is causality in the world of agents, right? Because there you have to think about ideas like what's the right reward to give? How should I create these maybe some constraints, testable constraints based on the SCM? Maybe that's a better reward to give than just give some standard RL reward. And also think of blame and all those things, right? So in an LLM-driven agent world, causality would be one of the most important things to get right. So people who are new perhaps should definitely look at that. And of course, if you're more interested in training, I think, of course, the short-term question is how do you make LLMs better through causality? And I think on the other side, I would say there's so much to be done for science in using LLMs. And so if you're more towards scientific causal inference, I think the best way to have impact today is to build tools that help scientists make better use of their data, make better use of their own literature, and then also propose experiments. All of it is possible. It seems like we're living in a fairyland right now, depending on the news and research articles. But some of it might be true, right? So maybe in the future, it's possible that LLMs can actually create graphs out of scientific literature. They can help plan new experiments. What we need then is for scientists to have the right tools so that they're able to do the cycle of science much faster, right? So I think if people are interested in the causality side, I would say that it's not just about doing one study anymore. I think that part, of course, you can do, but I think the ambit has become much broader. It's like we could actually help scientists do their cycle of science much faster.
Great, Amit. Thank you so much. That was a wonderful conversation, and I'm sure our audience will love it as well. Is there any last message that you would like to share before we close?
No. I think maybe I'll just put a plug, like for people, just mentioning again that PyWhy is an open organization. It's like we have under MIT license, all our software is open, so there's no sort of industry affiliation, right? Either with Microsoft or Amazon. So I think I would say if you're a researcher, if you're interested in causality, if you have interesting methods, please do consider contributing to all the repositories inside PyWhy. And of course, like if you have feedback, if you want to improve it in certain ways, if you want to take it in some directions, all of that is welcome. And I think we obviously, for example, I am the maintainer of one of the repositories, but by no means I control it, right? So if you come up with new ideas and you want to drive it forward, then I think we would welcome it. And you can actually become a core contributor as well. So maybe it's just a plug, right? So perhaps check out PyWhy, and if anything interests you, we are a very open community. We have a Discord that has about, I think, 800 users now. So if you have questions about causality, you can come there. More often than not, there are experts better than me who answer the questions. So you can check that out as well.
Great. And if I can add just one thing to this, I think not only researchers, but also practitioners who face challenges with causality in their work, I think would be very, very welcome in this community, because at the end of the day, their perspective is super valuable as well.
Definitely. Yes, definitely. In fact, one of the things that if any of our listeners can contribute, right, is about real world use cases of causality, right? So if you're working in healthcare, if you're working in, let's say, the social sciences, and you have an interesting use case, right? Even if you've not used PyWhy, you can come to us, and then maybe we can write some use cases with PyWhy, because I think that really motivates people to see the impact of all the different ways in which causality could be used.
Definitely. Amit, Thank you so much.
Thanks, Alex. Yep. Bye-bye.
Thank you.